Foundations and Laws of Thermodynamics. At 502, Chemical and Statistical Thermodynamics. Instructor Assoc, Montree, Sawangphruk. First semester, 2024. August 18th, December 20th, 2024. Overview of thermodynamics. Study of energy, work, heat, and their transformations. Open, closed, and isolated systems. Chemical reactions, energy storage, engineering systems. Classical and statistical thermodynamics. Energy conservation, heat transfer, and entropy. The 4 laws of thermodynamics. Zeroth law defines temperature and thermal equilibrium. First law, energy conservation, energy cannot be created or destroyed. Second law, entropy, spontaneous processes increase disorder. Third law, entropy of a perfect crystal approaches zero at absolute zero. These laws apply to all physical and chemical processes. Zeroth law of thermodynamics, no heat exchange between systems at the same temperature. If A equals B and B equals C, then A equals C, equilibrium. Allows for the concept and measurement of temperature. Basis for thermometry, temperature measurement. Systems in equilibrium with the same body are in equilibrium with each other. Temperature and thermal equilibrium. Measure of average kinetic energy of particles. No net heat flow between objects in contact. Heat flows from higher to lower temperature until equilibrium is reached. Two objects, initially at different temperatures, reach the same temperature when placed in contact. A tool that reaches thermal equilibrium with the measured object. First law of thermodynamics. Energy cannot be created or destroyed, only converted. Delta U equals QW. Internal energy change equals heat added, work done. Total energy contained within a system. Energy transferred when a force moves an object. Energy transferred due to a temperature difference. Energy transfer occurs without mass transfer. Internal energy, U. Total kinetic and potential energy of particles in a system. Depends only on the current state, not the path taken. Due to heat added or work done on by the system. Heating a gas in a closed container increases its internal energy. Internal energy is proportional to temperature in ideal gases. Heat, Q, and work, W. Energy flows from hot to cold objects. Energy transfer through force, such as gas expansion or compression. Describes how energy is transferred between heat and work. Heat added to a system, Q0. Work done by a system, W0. A piston compressing gas, work is done on the gas, increasing its energy. Applications of the first law. Convert heat into work, e.g. internal combustion engine. Work is used to transfer heat from a cold space to a warm one. Heat absorbed or released during reactions changes internal energy. Expansion of steam in a turbine, work extracted from energy. Batteries, solar cells, and fuel cells rely on energy conservation. Second law of thermodynamics. Measure of disorder or randomness in a system. Natural processes increase the entropy of the universe. Delta S university 0 for spontaneous processes. Heat flows spontaneously from hot to cold, never in reverse without external work. Irreversibility in real processes, limits of energy conversion. Entropy and disorder. Entropy is a state function that quantifies the number of possible microstates. More disorder, more possible configurations, e.g. gas molecules. Less disorder, fewer configurations, e.g. solid crystal. Melting ice increases entropy as molecules move more freely. Real processes that increase entropy, like heat conduction. Spontaneity of processes occurs naturally without external energy input, del S 0. Ideal processes where del S equals 0, no energy dissipation. Heat flows from hot to cold. Gas molecules diffuse to fill a container. Mixing two gases increases entropy. Requires external energy input, e.g. refrigeration. Gibbs free energy, G. Energy available to do work at constant temperature and pressure. GHTS, enthalpy, temperatures, entropy. Delta G, that's 0 for spontaneous force, G equals 0 for systems at equilibrium. Used to predict reaction feasibility in chemical systems. Examples of the second law. Work cannot be 100% efficient due to unavoidable entropy increase. Requires work to transfer heat from cold to hot. Reactions tend toward states with higher entropy. Theoretical ideal engine with maximum efficiency. Always involves some loss of usable energy due to entropy. Third law of thermodynamics. As temperature approaches absolute zero, the entropy of a perfect crystal approaches zero. Theoretical temperature where all molecular motion stops, 0 K. Have a single microstate at absolute zero, resulting in zero entropy. Absolute zero cannot be reached by any finite number of steps. Superconductivity, Bose-Einstein condensation. Behavior near absolute zero. the lowest possible temperature where molecular motion ceases. Study of systems at very low temperatures. Certain materials exhibit zero electrical resistance near absolute zero. Entropy decreases as temperature approaches 0 K. Low temperature physics, quantum phenomena. Thermodynamic properties. Enthalpy H, entropy S, and free energy G depend only on the system state, not the process. Measure of heat content at constant pressure. Measure of disorder or randomness. Useful for predicting spontaneous reactions. Useful for systems at constant volume and temperature. Enthalpy H, total heat content of a system U plus PV, H equals PV, where P is pressure and V is volume. Enthalpy change represents heat absorbed or released, used in phase changes, e.g. heat of fusion, heat of vaporization. Exothermic reactions release enthalpy as heat. Entropy and free energy, S and G, related to the number of microscopic configurations of a system, determines whether a process is spontaneous, del G 0. Relevant for constant volume systems, del A del 0 for spontaneity. Del G equals 0 at equilibrium. Used in chemical and biological reactions. Conclusion. Zeroth, first, second, and third laws of thermodynamics. Energy conservation, entropy and free energy. Energy systems, chemical reactions, low temperature phenomena. Molecular simulations, electrochemical systems, energy storage. Apply these concepts in problem sets and practical experiments.